How you doing? I'm Mr. Rose, and today we're going to do two things. Kind of the same example, just two different ways. We're going to look at the center of mass about something that has a uniform mass density versus something that has a non-uniform mass density. So that's kind of our goal. Obviously, we're going to start with the easier one, the uniform mass density. So I have a picture that I already drew out. That's I defined its length from 0 to L, as you can see. I also defined this small dx as I move along from 0 to L along my x-axis. This dx has some differential mass unit dm. My goal is to find the center of mass, and you should know, if this is uniform, this is a multiple choice question or just anything like that, that the center of mass should obviously be right in the middle, right? This should be my center of mass, and it should be at, let's say, L over 2, halfway down. So maybe I know that and I'm done. Maybe this question isn't find the center of mass, but prove that the center of mass for something that is a uniform mass distribution, like so, along the x-axis is at L over 2. So how exactly would I go about doing that? Well, things that I want to remember, I wanted to remind you that, so we're really going to find the center of mass by taking all the small parts that I have here from some reference point. Obviously, my reference point here is going to be 0. Then what I'm going to do, I'm going to add them all up from 0 to L to find out where my center of mass is, and I'm going to divide that by the total mass. So it's going to be nice and simple. And we should remember our antiderivative formula, right? The antiderivative from 0 to L of x dm over m, where m is the total mass, and obviously I can pull out that m, and I'm going to use that little trick that we were talking about earlier. I'm going to use what we're going to say our linear mass density, right? So I know that lambda is equal to m, that should be capital M, over L, which means I can say m is equal to, what is that, lambda times L? L times lambda. So I'm going to use that in some fashion here to make myself something simpler, something easy I can use, right? So remember, this lambda is my linear mass density. Basically, linear mass density, unlike volumetric mass density, right? This linear mass density is how much mass the object has per unit length. So it's really just the same thing we know as density. I'm going to take that, I'm going to sub this guy in. Oh, rephrase, I'm jumping ahead of myself. I'm going to take my object, I'm going to cut that rod into thin little discs that I got there, that dm, such that I can sub things in. So I'm going to take, right, so because I know my linear mass density, I'm going to take that dm, and I'm going to say dm is equal to dx times lambda. Now I could say the center of mass, my center of mass is equal to 0 to L of x over m times dx times lambda, right? Because my dm, I just subbed in dx times lambda. So now I can pull out my constants of, what do I want to pull out? I'm going to pull out a lambda and an m. So I'm going to have lambda over m times the antiderivative from 0 to L of x dx, x dx. Right? So now I'm going to take that antiderivative, so I can say my center of mass is equal to, my constants didn't change, lambda over m times the antiderivative of x is going to be x squared over 2. And we're going to go from 0 to L. Well, I know the zeros are going to cancel out, so I'm really just going to have my center of mass equal to lambda over m. That's still lambda over m. Right? Now I'm going to sub in my L squared minus 2 minus 0, so that's going to be times L squared over 2. And now my last step is, what was lambda? Well, we know lambda is mass per unit length. Right? So I'm going to sub back in my mass per unit length, so I can say my center of mass is equal to lambda, mass per unit length, and if we did this right, that should go away, times 1 over m times L squared over 2. My m's cancel, L cancels with L, and I'm left with my center of mass about the x-axis of L over 2. All right, so that was hopefully pretty straightforward and pretty easy. What if I have a different option? What if I have a multiple choice question? Same thing, except now I have a non-uniform mass density. Now, for multiple choice, technically I'm missing something here. I made up some options, and if the density of this object is going to change as x changes, clearly where I have it darker over here, that is trying to indicate that this is more dense than over here, and then where it gets lighter. So I have a changing density, and I would need some kind of a function. So that changing density, we're going to define as a linear density of A, where A is some constant, times x. Right? So my linear mass density is now dependent on x. And if I wanted to know where the center of mass was about this object, you might be able to just guess and move on. We know it's not going to be at 0. We know it's not going to be at L, which means I can get rid of those two. We know it's not going to be 1/2 L, because 1/2 L would be if it was the same as this one, where it was uniform. So we know it's also not going to be C. So that leaves choice D or choice B. Well, a quarter of the way from the lighter side, or where the density is less, that doesn't make any sense. The answer clearly has to be 2/3 L, right? It's going to be past center as the density continues to get more and more and more. Again, what if I needed to prove this? We're going to do everything pretty much the same, right? We're going to use the same method as we did before. We have this function that was going to be defined, and now we're going to take the same method. In other words, we're going to define small chunks like I did already in my picture as dm. So that means dm just like before. I'm not doing anything different, right? dm is equal to lambda dx. Now the only difference is lambda is not constant. Lambda is actually equal to ax. This actually may be going to be a little bit easier, right? If dm is lambda dx and lambda is a times x, that means I can sub in dm is equal to ax dx. How is that helpful to us now? Now I'm going to apply my center of mass equation like I did before. The center of mass is equal to the antiderivative from 0 to L of, just like we had before, x over m, x over dm, where dm is equal to ax dx, right? So now that is going to be, my center of mass is equal to the antiderivative from 0 to L of ax dx, and my m is a constant. If I want, I could take that out. My a is a constant. I can take that out. So that's going to be equal to a over m times x squared dx. Oops, drop my antiderivative. From 0 to L, the antiderivative of x squared dx, am. Now I know I can take my antiderivative here. That's a simple antiderivative. That's going to be equal to a over m of x cubed over 3 from 0 to L. And just like before, 0 to L, my 0 is going to cancel out. So that means my center of mass right now of my non-uniform object should be something like AL cubed over m over 3m, sorry, over 3m. So that is my center of mass, but it's not really it is still a function of length. So I don't know where it is, right? So what do I do with that? How do I, like, oh, the center of mass about the length is at some length? That doesn't really make sense. So what we're going to try and do is get rid of either this mass or get rid of this length. Like, right, one of them's got to be out of there. I want it about the length. I think I misspoke a moment ago. I want it about the length. I can't have it about the mass. The center of mass about mass doesn't make sense. So how do I get rid of that? What is m? Well, remember, m is just some small unit, right? I'm going to say m is equal to the antiderivative from 0 to L dm, right? Because as this thing moves out, as my small dx, this thing moves down, every dm is different. So mass, if I sum up all of those dm's, I get my total mass. We already know dm is equal to ax dx, ax dx, which means I can say the mass as this sucker moves down is equal to the antiderivative from 0 to L of just ax dx, which means my mass is equal to ax squared over 2 from 0 to L. Obviously, the zeros go away again, which means my mass is equal to AL squared over 2. Now, I'm cooking with fire. I've got this mass is a function of length. I've got a mass as a function of length, which means I can sub this into that. I can say my center of mass is equal to AL cubed over 3, right? AL cubed over 3. Now I'm going to sub this in for that mass times, let's see, I'm going to flip that in my head, 2 over AL squared, which means my A cancels, the cube cancels with the L squared, and now I have a center of mass equal to 2/3 times L. So we're going to clearly treat things the same. Everything's going to be done the same way, but we do need to exploit things that we know, right? So it seems like it might be a little bit of a cheat, but again, what did we do? This was easy. Nice taking a center of mass, uniform mass distribution. No real tricks except for that linear mass density. Here, once I'm done, like, oh man, I don't have I can't find the center of mass. Wait a second, center of mass about a mass unit. That doesn't make sense. So I've got to get rid of that mass, and I know as my length changes, my mass changes. So we're kind of applying the same thing twice. That's all I have for you today. I hope you found this helpful. Please feel free to like, click, and subscribe, and I'll see you folks next time.